No. Okay. Any questions about this particular program? The instructions, how to use a move long, to move from one register to another register. Okay. No particular questions? All right. So we talked about register, and I'm doing this a little bit, before it's time, because. Oh, okay. I just closed something I should not. And now it's time to. All right. So getting back to here, I think we covered sections 3.1 all the way up to 3.3 last time. So we'll go ahead and begin with other assembly language constructs. We'll start with memory sections. There are two memory sections. There are actually an infinite number of memory sections because you can define your own memory section in assembly language programming. I believe in Pragma, using Pragmas, you can do that in C and C++ as well. There's usually no need to do that in C and C++ programming, but in case there is a need, you can do that too. A memory section is nothing more than a contiguous area in memory, in RAM, when a program is loaded as a process. The concept of a memory section is necessary for several reasons. In the good old days, the i386 or the x86 processor has a concept of segments, so that's why there's the concept of a segment. A code segment is used to store instructions, and the data segment is used to store data, and also the system stack. The system stack actually can have its own segment too. The differentiation is needed to implement certain security feature. We talked about this already. The execution inhibit bit of newer Pentium and AMD processors basically says if there's any code in the data section, you cannot execute it. And that basically stopped all the buffer overflow exploits and all the stack overflow exploits, which were pretty common before that. And then once the processors can stop this, and the operating system has a feature to turn that feature on, then we can finally stop most of those ways to infect a system. Are there any questions about this particular statement? We kind of talked about it already, but I just want to make sure that people understand what that means. It's okay? All right. Now in this class, at some point, we'll kind of come back to the concept of what is a stack overflow exploit. When we start to talk about the stack and to talk about how you can overflow the stack with improper ways to treat an array, you can put an arbitrary payload into the stack, and by controlling the return address, you can actually have the program without this particular security feature. You can make a program return to the payload that is now on the stack, and then the malicious code gains control at that point. So we'll talk about that when it's time to talk about it. The assembler allows a program to define any number of sections. So in this class, we don't really need to do that. We just need to be aware of the two sections that we have to make use of. One section is called text, which is used for instructions. The other section is for data, and it's called a data section. To switch between the two, you just use dot data to switch to the data section. You can use dot text to switch to the text section. And you can switch around, you can switch between these two as many times as you want to. Now in this case, what is important is to remember whatever you specify here, okay, whatever memory content you specify here and whatever memory content you specify here, when the assembler is done and the linker is done, those two chunks of definitions will be contiguous because they both belong to the data section. Okay, so the dot text and the dot data, we call these directives. They're not commands, they're not instructions, they're called directives. What these are really doing is to say, oh, switch to the other book, switch to the other book. So so imagine that you have two binders, okay, one binder for dot text and one binder for dot data. When you say dot data, it's basically saying dot data becomes your active book. Whatever you write will be in that book. When you encounter the directive called dot text, it's saying, oh, okay, put the data book aside and switch to the text book. Okay? and then you continue to write on the textbook. If you say .data again, you put aside the textbook, you put your data book in front of you, and you continue from where you left off last time. So that's what these directives are actually doing. The term directive is referring to commands that are directed to the assembler itself. So they're not instructions. .data and .text by themselves do not generate anything in the object file nor the executable. They're basically instructions for the assembler, for the translator himself or herself. Is that okay so far? So it's not actually content intended for the processor or a part of the program. So even though the two .data portions are interleaved by a .text portion in this particular source code, the assembler actually takes the two .data portions contiguous, make the two contiguous in the data section. And the order is specific as well. This is going to have lower addresses, and this one will have higher addresses. Instructions should always be placed in the .text section. However, data definition can go to either one, because if you have strings that are read-only, they can also go to the .text section instead of the .data section. All right, memory allocation. Now, this one, has some of the syntax specification that we talked about earlier. A program can allocate memory for any section segment and initialize the memory allocation memory locations at the same time. This can be helpful to initialize variables in double quotes in a program. So what this will do, okay, let's try to understand this command or this syntax first. .int is not in angle brackets, nor is it in anything else. So it means it has to be entered or typed verbatim. So you have to type your .int, to start this particular directive. V1 is in angle brackets, which means it is just a placeholder. It has to be replaced by actual value, so that you can initialize memory locations using those particular values. The other part here, the curly braces are basically used to group things. So in this case, the curly braces is grouping two particular items inside. The two items inside include a comma. The comma itself is all by itself, which means it is also verbatim. You have to use a comma to separate multiple values. The V here is in angle brackets, which means it is another value. And then the asterisk symbol means whatever is before that can be repeated any number of times, including 0. All right? So together, what does this part of the syntax is really specifying? It is simply specifying you have to have at least one value, but then after that you can have any number of values. They have to be comma separated. This is not the full syntax, because the full syntax will also specify you can have any number of space between the values and stuff like that, but this is enough to give you an idea of how to use .int. An integer using .int is 32-bit. In other words, every item that you specify here, each one will take up 32 bits, 4 bytes. Are we doing okay so far with this particular directive? The next one is about the same thing, except we are dealing with 16-bit items. So each one will take up 2 bytes instead of 4 bytes. Dot byte, as the name implies, each one will take up only 8 bits or only 1 byte. Dot fill is an interesting one because it allows you to fill up a chunk of memory using a particular pattern. It allows you to specify how many items, what is the size of each item, and each item is going to have what value. So it allows you to specify repeating patterns if you want to. .ASCII gives you the ability to specify a string. Now you can always use .byte to specify a string, but it is very tedious to do so. Because if you use .byte to specify a string, then each character in a string requires 1 entry as a byte. Okay, you can use quote to get the ASCII code of a character, but even with that, it is still to spell a long string. It's still tedious. .ASCII just makes it not tedious to specify strings. The last one, .ASCIIs, is basically the same as ASCII, except it automatically appends a null terminator at the end of the entire string. It's mostly for programs that have to interact with C subroutines, because that's a de facto standard that C uses to terminate a string. Yep.
The documentation there, the dot is missing. Is that optional?
The dot is missing. Ooh, good catch. Okay, it is not intentional. It is a error. The next line does have the dot, but
I saw that. That's why I was asking if it's optional.
Yeah, that one should have a dot too. Yep. All right. Are there any questions about this particular screen? Now, I cannot write a sample program just yet to look at these things, because until we talk about labels, we can't really use the debugger and go to that location. I want to find out what is at that location. Okay, so we are not quite there yet. So just bear with me, because I think the next slide talks about labels. Labels, they're kind of like labels in C, where you're not supposed to use, right? So this is about the same thing, but it's not really exactly the same thing, because labels in assembly is very flexible. It's kind of like a combination of pound define, const, and also the regular label for gotos. Okay, it's kind of all of that kind of rolled into one single concept, which is very simple in a way. One of the most convenient features of an assembly language is the use of labels. A label definition can be just like that. In other words, you give it a name, and you put the equal sign, and then you give it a value. It doesn't generate any code for the processor. In other words, this is really another directive. It is helping the assembler itself to say, from here on, when you see this particular label, when you see references of this label, replace it with the definition, the value that is defined to. So in that sense, it's kind of like pound define in C and C++. How many people know what is pound define in C and C++? Because it's kind of like a deprecated feature, and a lot of professors do not like to talk about pound defines anymore. Okay, so you know what a pound define is? Okay. Sorry?
I've used it, but I'm not across clear on what it does.
Okay, pound define in C and C++ is a macro feature, which is it's handled by CPP, which is the C preprocessor. The C preprocessor, as the name implies, it does the processing before the compiler does. So when you say pound define, XYZ space 5, it will literally go through the rest of the program, and whenever it sees XYZ, it will replace it with the definition, which in this case is 5. But it is not very smart, which is sometimes a good thing, because whatever the definition is, it will just do it in text. It doesn't have to be a number. In other words, you can say, okay, some people do this, pound define begin, and then the open curly brace. And that's perfectly fine. Because what happens is, when the C preprocessor processes the rest of the code, whenever it sees the word begin, it will replace it with the open curly brace. So now you can use begin and end instead of open curly brace and close curly brace.
That's a pain.
It's for Pascal addicts, because they like begin and end. Or for Visual Basic addicts, you can always define end if, pound define end if, and then don't specify anything. So what that means is end if has no meaning, but in the eye of a VB programmer, they will still